Yeah. Good evening, all. Greetings. This is Dr. P. Ravindra Kumar. In the last class, that is lecture 5, we have covered the energy in state and in transition. Let me briefly go through the last class lecture, that is lecture 5. So, in lecture 5, I have discussed the energy in state and in transition, types of work, that is mechanical form of a work, non-mechanical form of a work. Next, heat, point and path function. Point and path function. So just briefly going through that one. So from that particular lecture, it is the student is expected to understand the heat and work interactions with the system and the surroundings. So what is meant by energy and what causes the driving force for the energy transfer? Next, after then, what are the static forms of energy and the dynamic forms of energy? How the macroscopic energy is contributing to turn the wheel, and what is the importance of this microscopic kinetic energy in the thermodynamics? The difference between the heat transfer and the work transfer. So when any energy interaction is taking place with a driving force of a temperature difference, then it is nothing but the heat transfer. Otherwise, we will call it as a work transfer. Energy in store, where it can be the microscopic mode or it can be the macroscopic mode. So the energy in transit, both heat and work are energy in transit, because these two are going to occur at the boundary of a system. And moreover, it is an inexact differential and it depends on the path of the system. So energy can be transferred only when a driving force or a potential is going to exist. And what are the various forms of a work in the last class we have covered? That is displacement work, electrical work, shaft work, surface film work, work done in stretching a wire, magnetic solid, and the non-mechanical forms of a work, polarization work, electrical work, magnetization work. Whereas the mechanical forms of a work, shaft work, paddle wheel work, shaft work, paddle wheel, these are the mechanical forms of a work. Work done in changing the area of the surface film, work done in stretching the wire. So work done in stretching the wire, where a student has to use this particular formula, where A is nothing but the area of the wire, E Young's modulus, L length of the wire, change, that is the strain, that is once the change in length is appear, the change in strain, epsilon 2 square minus epsilon 1 square. So this is the formula you have to apply for solving the work done in stretching the wire. Next, there is a flow work. So the flow work is nothing but PV work. Flow work is nothing but the PV work for a open system, and here the mass flows are entering and mass flows are leaving. So the dW, that is inexact differential, d bar W flow, that is nothing but the PdV, and how that it can be, see here, this is a capital V and this is a small v. Observe that. So the workflow through the open system, it is going to come out as PV work, right? So this d bar W flow is nothing but equal to P small v into dm. This is nothing but the specific volume meter cube per kg, and this is in kg, right? So this is how we are going to get the flow work. And once all these work transfers are discussed, then we have discussed the various process, that is constant pressure process, constant volume process, isothermal process, polytropic process, adiabatic process. All these are nothing but the reversible process. There are the two processes which comes under to this irreversible process, like free expansion with zero work transfer, that is we can call it as the free expansion process. Second one is the throttling process, where in a irreversible process, the line that is on a PV plane, when the system changes from state 1 to the state 2, you have to represent that in terms of a dotted line. Whereas in a reversible process, when a system changes from state 1 to the state 2, that it is the process is represented by a continuous line. So continuous firm line, FIRM, continuous firm line. So the throttling process means when a flow experiences the reduction in pressure passing through a narrow restricted space, then the reduction in pressure is going to take place. That means from the throttling process, the enthalpy of the fluid remains constant. H1 is equal to H2. That is enthalpy. Enthalpy of the fluid remains constant. See here, in a throttling process, it is represented as a dotted line because it is a irreversible process. It is a irreversible process. So in this case, both the potential energy and kinetic energies are neglected. So finally, this H1 is nothing but equal to H2. And after then we have gone through the heat. What is the driving force for the heat transfer? The temperature is the driving force for heat transfer. And this heat transfer can be, the mode of heat transfer can be divided into three ways. That is the conduction, convection, and radiation. The conduction heat transfer occurs between the two same bodies, whether it that is in two metallic surfaces, the heat transfer is going to occur. So that is nothing but the conduction heat transfer. When the heat transfer occurs from a metallic surface to the surrounding fluid medium, it is the convection. When the heat transfer occurs in terms of the electromagnetic waves, then it is nothing but the radiation. So always the direction of the heat transfer is from high temperature body to the low temperature body. So when the heat is entering into the system, it is positive. Heat leaving from the system, it is negative. So in the same way, work done by the system is positive. Work doing onto the system is negative. So the heat is a form of energy in transit and which is occurring at the boundary phenomena. Next, after then, there is a diathermic wall is there and adiabatic wall is there. Adiabatic wall is nothing but no heat transfer. Diathermic wall is nothing but it allows the heat transfer. After then, we have covered the specific heat and the latent heat. So the specific heat of a substance is defined as the amount of heat required to rise a unit mass of a substance through a unit temperature rise. So this is represented as the symbol C. So that's why most of the times we may write Q is equal to mc delta T, where C is nothing but the specific heat, M is nothing but the mass of the substance, delta T is nothing but the change in temperature. So the product of the mass and the specific heat, you can also call it as the heat capacity of the substance. So this C, if the process is occurring at constant pressure, you can represent it as a Cp, specific heat at constant pressure. If the process is occurring at constant volume, then you can write it as a Cv, that is the specific heat at constant volume. Next, once the sensible heat is there, so this heat can be classified as a sensible heat and the latent heat. So the latent heat is nothing but amount of heat transfer required to change or to cause a phase change in unit mass of a substance at a constant temperature and pressure. This is what you have to observe. So the latent heat is nothing but amount of heat, the amount of heat transfer required to cause a phase change, that is from solid phase to the liquid phase or from the liquid phase to the gaseous phase. So in this case, certain amount of heat transfer is required. So the amount of heat transfer required to cause a phase change in unit mass of a substance at constant pressure and temperature. Next, after then we have discussed the heat. So this heat can be, the latent heat can be classified as the latent heat of fusion, latent heat of vaporization, latent heat of sublimation. So this is the latent heat here. A phase change is going to be occurring from the solid phase to the liquid phase. So the melting and fusion is there. Melting is nothing but conversion of a solid to the liquid state. Fusion is nothing but conversion of a liquid to the solid state. Whereas the vaporization, or you can call it as the evaporation, conversion of a liquid phase to the gaseous phase or to the steam phase, conversion of a liquid phase to the gaseous phase at constant temperature and pressure. That is nothing but the latent heat of evaporation. The opposite of this evaporation or vaporization is nothing but condensation. the amount of heat required to convert gaseous phase from the gaseous phase to the liquid phase is called as condensation. So the opposite of vaporization is nothing but condensation. The opposite of melting is nothing but fusion. And there is sublimation, conversion of a solid state to the vapor state. So example you can consider for the sublimation is nothing but camphor, where camphor is nothing but the solid state. When you keep the camphor or solid carbon dioxide, it converts the solid state to the vapor state after a few days. So conversion of a solid state to the vapor state is called as a sublimation. What is the opposite of this sublimation? Frosting. In a refrigerator, when you frequently open the door, air is going to enter into the refrigerator, and that air is come out as a frozen substance. That is, it is nothing but frosting. So lumps of a solid is going to be accumulated inside the refrigerator, so that you can call it as a frosting. Right? Conversion of a gaseous phase to the solid phase is nothing but frosting. So that's why frequently for every 15 days or for every 2 weeks or 3 weeks, we will defrost the refrigerator so that the solid state will be converted to the liquid state. So this is how the heat is occurring. And already we have discussed the qualitative distinction between the heat and work. So qualitative distinction means all the work can be converted to the heat, and all the heat can be converted to the all the heat cannot be converted to the work. All the work can be converted to the heat. Say suppose if you are supplying 100 watts of a work, and you can easily convert that into 100 watts of a heat, but you cannot convert 100 watts of a heat into 100 watts of a work. So that is the qualitative distinction between the heat and work. System and the surroundings interaction in a process involving many energy flows. So when heat is entering, so here you just observe that when heat is entering into this side, that is what is that? Here some Q1, Q1 is leaving, and this is Q2, heat entering, Q3, heat entering. So that's why Q2 plus Q3, it is positive. Heat is leaving from the system, that's why it is a minus sign, minus Q1 is equal to the change in internal energy or the change in energy of the system, that is the delta E. That this delta E is nothing but total energy we can call. This total energy is nothing but the microscopic energy plus macroscopic energy. So the microscopic energy is a U, right? And the macroscopic energy is nothing but kinetic energy and potential energy, right? So when you deal the thermodynamic problems, whether it is a microscopic energy or it is a macroscopic energy, that you should have to be much more careful about this particular point. Next, work W2. What is this W2? The W2 is nothing but work done by the system. It is positive. W3. Here, this is also work done by the system. It is W3. What is W1? Work giving to the system. It is minus. Work input given to the system. And what is this one? Work input given to the system. So W4 minus W4. So this is how the distinction between the qualitative distinction between the heat transfer and the work transfer. So at the end, the point and path function is discussed here. So the point function is nothing but it depends on to the initial and final states. Point function is nothing but a property of a system depends onto the initial and final states of the system. That means you can write it as a exact differential, that is dV is equal to V2 minus V1. So this one V2 minus V1, or in the same way ds, that is change in entropy, is equal to S2 minus S1, or change in internal energy, that is du, is equal to U2 minus U1. So like that one, the enthalpy, change in enthalpy is equal to H2 minus H1. So in that way, where you can write the point functions, that is exact differential, it depends only on to the initial and final states of the system. Whereas the path function, so this work and heat transfer depends on to the path of the system, what kind of a path it is following, whether it is following the path A, or it is following the path B, or it is following the path C. So it depends on to the path of the system. So that's why these are the inexact differential, and the inexact differentials are represented as the d bar w, d bar q. So this is how the things are going to be kept in thermodynamical cases. So what is the distinction between the exact differential and inexact differential? So the exact differential dV is equal to 1 by P of inexact differential, that is d bar w. So this is how you are going to distinguish between the exact differential and inexact differential. Finally, the cyclic integral of any change in property, that is a change in volume, change in pressure, that is nothing but equal to 0. So this cyclic integral of this is going to denote the cyclic integral for a closed path, for a closed system, that is for a closed path. Therefore, the cyclic integral of a property is always 0. So this is what it is covered in the previous class. It is covered in the previous class. Now, in the lecture 6, I'm going to cover the zeroth law of thermodynamics. So the basic fundamentals are completely covered. The basic fundamentals, that is what are the terminologies connected to the thermodynamics, and how these interactions are happening from the system to the surrounding. All that particular basic terminologies are the basic concepts we have covered in the first half of the unit. So this is the second half of the first unit, that is the zeroth law of thermodynamics. Zeroth law of thermodynamics. So in this zeroth law of thermodynamics, the contents which are going to be covered as zeroth law of thermodynamics, concept of a temperature, what is meant by principle of a thermometry, reference points, constant volume gas thermometer, and scales of a temperature. So these are the contents which are going to be covered into this particular PPT, into this particular e-content. So after studying this particular content, at the end of the content, the student is expected to learn understanding the zeroth law of a thermodynamics. Understanding the zeroth law of a thermodynamics. So this is the second Bloom's level. There are, normally the student is expected to check at the various Bloom's level, that is the remembering level, understanding level, applying level, analysis level, design level, creation level. So this is how the students are going to be expected in various Bloom's taxonomy level, right? So after studying the particular content, whether the student remembering the concepts or not, that is the student is checked with the remembering power, checked with the understanding level, checked with the applying level, how strong he could be able to apply the basic fundamentals to solve the numerical problem. So here this is going to come as the understanding the zeroth law of a thermodynamics. So in zeroth law of thermodynamics, what is the significance here? So normally what we may think that the first zeroth law is the first law, after then the first law is there, next second law. So hierarchy or the order point of view, we may consider that zeroth law is the first connection, second one is the first law. That is how we may treat or we may think. But you just observe, the zeroth law was first formulated and labeled by R.H. Fowler in 1931. But whereas the first law of thermodynamics and second law of thermodynamics already gave much more concepts in 19th century, that is the 18th and 19th century. So 1780s, 1780, 1850. So in that period, already the several problems have been solved. So the zeroth law was first formulated and labeled by R.H. Fowler in 1931. The property which distinguishes from the thermodynamics is nothing but here the temperature. So the point which you have to understand in the zeroth law of thermodynamics is nothing but the temperature. The temperature is the property got its birth from the zeroth law of thermodynamics. So temperature is associated with the ability to distinguish the hot and coldness. Temperature is nothing but it is associated with the ability to distinguish hot and cold. Normally, the perception whether it is a hot condition or in a cold condition, just only that is the information. So, according to the thing, when two bodies, see here, when two bodies, that is the iron body and copper body, when two bodies at different temperatures are brought into contact, after some time they attain a common temperature. Iron is also going to reach the 60 degrees centigrade, copper is also going to reach the 60 degrees centigrade. So when two bodies are brought into contact, after some time they attain a common temperature and are said to exist in a thermal equilibrium. So this is what the zeroth law of a thermodynamics. In another way, you can define the zeroth law in such a way that when body A is kept in contact with a body B in thermal equilibrium, when body A is in thermal equilibrium with a body B, and separately the body C, then the body B and C will be in thermal equilibrium with each other. This is known as the zeroth law of a thermodynamics, and it is the basis for the measurement of a temperature. When body A is in thermal contact with a body B and separately with a body C, then the bodies B and C will be in thermal equilibrium with each other. This is known as zeroth law of a thermodynamics, and it is going to form the basis for the measurement of a temperature. So at that point, the heat transfer is going to stop and the two bodies are said to have reached the thermal equilibrium. The equality of temperature is the only requirement of a thermal equilibrium. The equality of a temperature is the only requirement for thermal equilibrium. So this is the basic definition of a zeroth law of a thermodynamics. This is the basic definition of a zeroth law of a thermodynamics. Now, once it is standardized, then we have to learn the concept of a temperature. What is meant by a principle of a thermometry? What is meant by principle of a thermometry?